Hi. Okay, now we're ready to learn how to solve first order linear differential equations. And so we want to figure out a method that works on every first order linear differential ODE, so that even if it has an inhomogeneous term, that we can work out, or at least in principle, work out the exact solution. So let's look at how to do that. Okay, so I'm going to write my linear first order ODE in a slightly different form than I wrote it in the last video. I'm going to write it with the coefficient of 1 in front of y prime. So divide by something if you need to get y prime by itself, and then we'll call the coefficient of y, we'll call that p, and the coefficient of the inhomogeneous term we'll call little q. And we only show you tricks that do work. It would be silly to show you tricks that people tried that didn't work. So here's the trick. We want to find a function mu of x so that d mu of x, the derivative of mu with respect to x, is mu times p. Okay, so I'm not writing the of x anymore. Now that seems strange. You may say, why in the world would you want to do that? And the reason we want to do that, well, it shouldn't be because I'm just going to say because. We want to do that because if we multiply, let's call this 1. If we multiply 1 by mu, we get mu y prime plus mu p y is equal to mu q. Okay. And now if this is true, then let's look at what do you get when you take the derivative with respect to x of mu times y. Now, what would you get if you took the derivative? Well, by the product rule, I would get mu times y prime plus mu prime times y. But what is mu prime? Mu prime, by this by the what we said we want to have, this is mu prime. Mu times p is mu prime. So this left-hand side right here, all together by the product rule, is exactly d by dx of mu times y. And so that's equal to mu times q. So why are we any better off with that? Well, that says d mu y is equal to mu q dx. And remember, these guys over here are functions of x only. Okay. And this is like the derivative of anything. It's the quantity mu y. It's a perfect derivative. So these variables are separated. We can integrate on both sides. When I integrate on the left, I get mu times y. When I integrate on the right, I get whatever I get. Okay, so I get the integral of mu of x times q of x dx. So one of the one of the caveats in this method is, are you getting something you can integrate here? If not, you can only express it as an integral and you can't say exactly what the solution is. Not the best thing, but it's not terrible. Okay, and then to get y, all you have to do is divide by mu. So y is 1 over mu of x times the integral of mu of x q of x dx. Okay. And notice that's an indefinite integral, so you will get an arbitrary constant from that. And one arbitrary constant is exactly what you expect for a first order equation. Okay. All right. So if we can find something that satisfies this condition boxed in the pink, let's call that one 2, then we're in business. We can write down the solution. This solves the equation y prime plus p of x y is equal to q of x. Okay. So in a way, you might think, well, we traded one problem for another, except that we can say a lot about solving this. This should look very familiar. So let's look at solving equation 2. Okay. So now to solve equation 2, that's separable because we can write that as d mu over mu is equal to p of x times dx. Remember, mu and p are both functions of x. So we can integrate on both sides because we've separated the variables. When you integrate d mu over mu, you get ln absolute value of mu. When you integrate p, you get whatever that is. Okay, so another caveat, can you integrate p? We have to see. Now that's not quite what we wanted because we wanted to solve for mu, not the log of mu. So we have to use our rules of calculus and the fact that the exponential and the log are inverse functions. Okay. To say that so basically you have to get the log out from being trapped in the, you have to get the mu from being trapped inside the log. So the way you do that is you exponentiate. Hopefully you remember that from calculus or really from algebra. Okay, and E and ln are inverse functions. So this gives you mu of x. And so mu is e to the integral p of x dx. Okay. And so that's the mu that satisfies condition 2. So actually, in fact, we don't really need to you don't have to go through this calculation all the time. You can just remember that this is the trick. You find e to the integral p of x. So remember where p came in. Let's go back. So we started with our equation here. The trick was to find a mu that satisfied this, because if we did, our solution was given this way in this integral formula. And then we worked out that to have 2 satisfied, all you need to do is pick mu exactly this way. Actually, this mu has, these kinds of things have a name. They're called integrating factors. This is the one that works for linear equations, but in a few sections, we'll look at integrating factors for nonlinear equations too. Okay, and basically that's it. Now we just have to work it out. So let's do a couple of examples and see this thing in action. So let's see. Let me look at, I had an example I wanted to do, I had in mind. Suppose we look at x times y prime plus 2y is equal to 4x squared. And let's give an initial condition. Let's say y of 1 is 2. Okay. All right, so we want to solve. So to solve it, we notice it's linear. And so what do we have to do to use our method? Well, we have to get that coefficient in front of the y prime term to be 1. So I divide the equation by x. Okay, so when I do that, I will get y prime plus 2 over xy is equal to 4x. Okay. All right, so now we have it set up because this is y prime. Here's our p of x, y, and here's our function q of x. Okay. So now the method that we just learned is you find the integral, find the integrating factor. And for linear equations, the integrating factor is always the same. It's e to the integral p of x dx. Okay, so that's e to the integral. In this case, p of x is 2 over x dx. Now, when you integrate 2 over x dx, well, that's 2 times 1 over x dx. So hopefully you remember that 1 over x integrates to e to the absolute value of ln x. You don't need to worry about the plus c because it just changes everything by we just need one integrating factor. We don't need every integrating factor. So you don't need the plus c. Only need one. So we can ignore the arbitrary constant c, okay, at this stage of the game. And now what? Well, that's not the prettiest form you've ever seen, so you got to do a little bit of work. So this is going to be e to the ln x squared by properties of logarithms, because r ln a is ln of a to the r. And you need to do that because the only way to use the fact that e and ln are inverse functions is if the e is getting directly applied to the log of something. Here, you can't do anything because the 2 is essentially in the way. Okay? So now e and ln are inverse functions. That means it wipes each other out. So our integrating factor is x squared. So this is our integrating factor for our problem. Okay, so now what do you do with the integrating factor? Once you have it, let me see if I can balance all of this. It's a little bit the tight position where I have things written, where I'm working. So let's just remember that the integrating factor is x squared. So now I'm going to take my equation, the one with the y prime by itself in the front. Don't go back to the first one. You need the one with y prime. Now we multiply y prime plus 2 over xy equal 4x by x squared, which was our integrating factor. So I'm multiplying the whole equation by the integrating factor. So we will get x squared y prime plus 2 times x y is going to equal 4x cubed. Okay. All right. Everybody with me on that? Okay. And so now, now what do we do? Well, we know that we pick that integrating factor so that this left-hand side is a perfect derivative. And what is it a perfect derivative of? It's a perfect derivative of the integrating factor times y. So that's x squared times y in this case. It was mu times y. Now let's double check to make sure that this derivative really is this left-hand side. Okay. So by the product rule, that's x squared times y prime plus 2x times y. And that's exactly what we have. Okay. So it worked like it was supposed to. And this is equal to 4x cubed. Okay. And now we just multiply by dx. Okay. And notice this is a perfect derivative. It's like saying dr. When you integrate dr, you get back r. Well, it's d of this quantity. So that's a perfect derivative. And this side we can integrate. So we integrate both sides. And like I said, if you think of r is x squared y, and then you have the integral of dr, what would you get? When you integrate that, you would get back r, which in this case is x squared y. And when you integrate 4x cubed, you get x to the 4x to the 4th over 4. So that's just x to the 4th plus c. Now you need the plus c because you need all the solutions, not just one. Okay. And now we can solve for y by just dividing by x squared. So y is equal to x squared plus c over x squared. Okay. So this is the general solution of our ODE example. Now we are not done because we haven't made it fit the initial condition. So let's make it fit the initial condition. We need y of 1 equals 2. So that says you go in this formula, you let y be 2 when x is 1. C over 1 squared. Okay, so that's 2 minus 1 is 1. That's just C. So C is 1. Okay, so the final answer is y is x squared plus 1 over x squared. And that's your solution. Whoops, I got one a little low. So basically, you do for first order linear equations, you do the same thing all the time. You find the integrating factor, and the integrating factor is always e to the integral p of x dx, where p is the coefficient of y. And then just work through, don't try to memorize that solution. There's going to be too many things to memorize or look up. You multiply the equation by the integrating factor. That should give you the perfect derivative on the left-hand side of the integrating factor times y, and you can check that. And then whatever you got on the right, you have. You just have to integrate. Okay. All right, let's try it again with another one. Let's try, oops, okay. Here's another example. Suppose I take, now let me be careful. I have an example written here that I wanted to do. Okay, let's look at an example here where we will take x times y prime plus y is equal to x ln x, and y of 1 equals 0. Okay. All right. So sorry about that shadow there a little bit. Okay, so the first thing we have to do is get the y prime term by itself. So we will divide by x. Okay. And now here's my p of x. And here's my q of x. Okay. So I find my integrating factor. It's e to the integral p of x dx, always. Okay, so here that's going to be e to the integral 1 over x dx, which is e to the ln absolute value of x, which is, because these are inverse functions, it's just x. Okay, they cancel each other out. Okay, all right, and now, so we have our integrating factor. So what do? Now you multiply the equation by the integrating factor. And then get to work. Okay, so I'm going to multiply this equation, the one that has the 1 in front of the y prime, by the integrating factor. So I will have xy prime plus y is equal to x ln x. Okay, interestingly, that's what we started with. And now this on the left-hand side better be the perfect derivative of my integrating factor times y. Okay, let's check. If you differentiate this product, you will get x times y prime plus y. So yeah, that is, this left-hand side is exactly this. Whoops, can't see it there. Okay, it's exactly the integrating factor times y. All right, and so that's x ln x. So now we just multiply through by dx. You notice we're doing the same routine every time. Okay. And now we integrate on both sides. Okay, on the left-hand side, it's a perfect derivative, so you just get x times y. On the right-hand side, what do you get? Well, this is where you start seeing how Calc 1 and Calc 2 keep popping up. This is an integration by parts problem. And so you need to know how to do that, or you're stuck way back here. So you let u, be x, and du is dx, and dv is ln x dx. Oops, sorry, that's backwards. It's ln x, and then du is 1 over x dx. Sorry, backwards. And then dv is going to be x dx, and v will be x squared over 2. Okay, and remember the integration by parts formula is the integral of v du, u dv is the way most people memorize it. It's uv minus the integral of v du. It's really the product rule, but anyway, that's how we do it. Okay, and so so now this is going to be using integration by parts. U times v, so that is x squared over 2 ln x, minus the integral of v with times du. So du is 1 over x dx, v is x squared over 2. So this will be, there's a minus sign out in front, so that will be x over 2 dx. Okay. All right, and so now we're one step away from almost near the finish. So this is x squared over 2 ln x. If you integrate this, you get minus x squared over 4 and a plus c. Okay, and now to get y by itself, to get our answer, we just divide by x. So we have x over 2 ln x minus x over 4 plus c over x. Okay. And so that's our general solution to the ODE. We must work out that initial condition in a minute. Okay. Now, one of the cool things about ODE is once you get your answer, you can always check it. How can you check it? Differentiate it. See if it satisfies that equation. If it does, it was the right answer. And if it doesn't, you made a mistake. Okay. All right, so now let's go on and find our specific solution, our particular solution that satisfies the condition y of 1 equals 0. So we have y is x over 2 ln x minus x over 4 plus c over x. And we want y of 1, sorry, to be 0. Okay. So that says that 0 better be equal to 1/2 ln 1 minus 1/4 plus c. Okay, but ln of 1 is 0. So that says c minus 1/4 is 0, so c is a 4th. Okay, so then our explicit solution is x over 2 ln x minus x over 4 plus 1 over 4x. Okay. Okay, so the routine's always the same. The integrals you'll have to evaluate vary from problem to problem. But that's it for the method for linear equations. Okay, on to our next section.